Thank you. I'm presenting today. I was formerly the application director for GE, did a lot of these tech talks, and we had a lot of requests for a tech talk around the thermal model when I don't have a lot of good data. And since we had so many requests there, I didn't leave that one hanging, so I agreed to do this one. And so that's what I'm going to do today. Now, what I want to do today is I'm going to start out and I'm going to talk a little bit about the AC model and some of the fundamentals, because we really ought to review those fundamentals before we jump into this. And that's what we'll do first, right? And then we're going to jump into how to set the thermal model with very limited data. And so we're going to have to make some assumptions. We're going to have to do some things. We may have to do some testing, but nonetheless, that's what we're going to do. And then we'll sort of conclude with what GE's motor protection offerings are and what you can do there. And we'll have some conclusions. So let's jump in and talk about the motor thermal model and do some fundamentals. Now, before we do that, let's have a few caveats and some disclaimers, right? So this presentation, it's based on how to set the thermal model if you have very little data. Several tech talks on the thermal model. I've done one, Christine Kreitz has done one. Those are both great tech talks around around the thermal model. The one that I did was around the actual thermal model, and the one that Christine did was around how to the thermal lockout associated with the thermal model. Now, both of those tech talks are available on demand from the resources page, and I think that those were sent with the registration link, and if not, we'll make sure that you have access to those. So it's not necessarily a prerequisite for today, but it would help immensely if you had viewed those in the past or have some understanding of the motor thermal model and how it's set inside of GE relays to understand how we would set this if we don't have a lot of data. So again, what I'm going to present today, this is not a shortcut. This is not a shortcut. You should do your due diligence and try to set the motor thermal model based on the motor data. And if this is only meant to give you some guidelines or a best bet when there's no data available. Without proper data, these techniques cannot be totally relied upon to protect the motor. So you should think of this as a best bet to protect the motor when you don't have good data. So one of the things we'll have to assume is, for our purposes today, we'll assume that you have a motor nameplate. And from that motor nameplate, we should be able to set most of our items. And then we'll have to do some other things, some other innovative things for the other items. Now, one of the other things that I should say is if you've got an existing motor, you should make every attempt to reuse the protective data that you have on that motor. So if you've got an older electromechanical relay, an older electromechanical relay or electrothermal relay, that relay will have settings around the pickup. It'll also have some settings around the curve. And it's not really settings if it's electromechanical, but it's the same thing as settings. You should reuse those as much as you can, because that device has been protecting that motor for some time, and you should reuse those. If you have a microprocessor-based relay and you're upgrading your relaying to a new microprocessor-based relay, you should utilize the settings that are in that microprocessor-based relay today to protect the motor with the new microprocessor-based relay. So as much as possible, if you don't have good data, reuse the existing protection settings. So let's review real quick about the thermal model. Now, the best analogy for this that I have is this diagram that we've used for years. And it's basically The red lava-like fluid on the far left of the picture I have there, that represents a modeled thermal capacity of the motor. And what the relay is going to do is it's going to model the thermal capacity of the motor. And the thermal capacity used is expressed inside of the protective relay actual values as thermal capacity used. And it's expressed as a percentage. And so when you exceed 100% of the thermal capacity used of the motor, you can imagine the red lava-like fluid would exceed the capacity of the beaker that it's flowing into in this picture. And in that case, that's when you would have a trip. So the relay, the protective relay, models the thermal capacity based on a lot of different things. So it will model that based on the current. It will model that based on the unbalance of the current. And then you really need to know if the cooling is available on the motor and if you have an unusually high ambient. And the motor thermal model can be biased with RTD biasing, and that would take care of an unusually high ambient or the loss of cooling on the motor. And so those things can all be brought into the motor protective relay and allow the motor protective relay to build this motor model and model the thermal capacity used. And again, when you reach 100% of that thermal capacity used, you have no more thermal capacity left in the motor, and that's when a trip occurs. Now, the presentation that was previously done, and it's available that Christine Kreitz did, was about how you would have to restart that motor, or how you can restart that motor after you've had a trip, and how the relay models how that thermal capacity uses decays over time and has to decay to a value that the relay will allow a trip. And that's a great presentation. I highly recommend that you view that presentation to understand how the motor thermal model is, the cooling is basically calculated. Okay. So there are several settings, and the settings that I'm showing here right now, these are settings that are available in the 869 relay. And these are two places that you will find these settings. One of the places is under System Setup, and it's the top window, which is the motor settings. And then the window that's underneath is found under the protected settings, and it is the thermal model settings. And there are the settings that are going to be necessary to build the thermal model are listed over on the left, with the two most important things being the overload pickup level and the overload curve. And so if we look at how those things map out, you can see that we're going to set the overload pickup level in the motor settings, and that's where we're going to give it a setting of overload factor. We're going to set an overload curve, and that's in the 869. That's called a TD multiplier. If the overload type is set to motor, that's the second setting from the top on the thermal model there. If it's set to motor, that TD multiplier corresponds to standard overload curves for motors. And then there's going to be a couple of settings that we need to give the relay to let it model how fast the motor will cool when it's stopped and how fast the motor will cool when it's running. And those two settings are called running and stopped cooling time constant. And I'm really stressing the cooling time constant here because that is the cooling time constant, which is going to be 1/5 of the cooling time. We got some slides on that a little bit later. The previous presentations we've done, go through this in detail, but it is very important to note that that is cooling time constant. There's also a setting that's used in the motor thermal model called the hot to cold safe stall ratio. Hot to cold safe stall ratio is used by the motor thermal model to model where the thermal capacity falls to when the motor is running under its normal conditions. So when it's running at its rated temperature rise, that would be the amount of thermal capacity used. It relates to the amount of thermal capacity used at that point. And then something that's going to be very important, especially for these motors that we don't have a lot of good data on, is the RTD and unbalanced biasing, especially the RTD biasing, and I'll talk about that a little bit later. But those are the RTD and the unbalanced biasing are both ways to bias the motor thermal model based on the measured temperature from the RTDs or the unbalance that is associated with the measured currents. All right, so we have a poll question. So here we go. When does the current-based thermal model start to accumulate thermal capacity used? So please, well, I think this is the first time we've done a poll. So please make your choice. And if you've watched the prerequisites that I've mentioned earlier, you should know the answers here. So this will tell us who has watched the prerequisites. All right. When does the current-based thermal model start to accumulate thermal capacity used? So 38% of you said always. 0% said never. That's good. When the current is above pickup, that's a good answer, 38%. When the measured RTD temperature is above ambient at 14%. And all of the above said 8.2%. So somewhere about 8.2% of you don't know the difference between always and never, right? Because those two are mutually exclusive. But all of the above is a really close answer. And the reason it's a really close answer is because it could have been C or D, right? So the relay starts to accumulate. And accumulate means that it's getting bigger, right? So it's accumulating and getting more thermal capacity used. Now, it'll generate a lot of thermal capacity used during a start, but when it's normally running, it will start to accumulate thermal capacity when the current is above the pickup. And when current is above pickup, it will start to accumulate thermal capacity. And if we leave that current above pickup for long enough, it will eventually trip on the motor thermal model. Now, the reason that D was a good answer also is because if we're using RTD biasing, we'll start to accumulate thermal capacity used in that alternate thermal model with the RTD biasing when the measured RTD temperatures are above ambient. But that's only if we're using the RTD biasing, and it's only if it's when it's above the ambient. Okay, so in an ideal world, you get this curve right here. You get this on a data sheet. And if you get this on a data sheet, then, life is good because you can set, in a normal situation, you can set a standard motor, a motor protection curve just below A, right? So A, the curve A there is is the cold running overload. So that's a cold curve. Curve B is the hot running overload curve. So you would set it just below A and C. And so C is the cold locked rotor curve. So that's where you're going to create damage during a start. and then A would be where you would create damage when it's running normally. And I would want to place that just below A and C, a standard curve there, rather than just below B and D, because B and D are the hot overload curves. And we don't really need to protect for those because the lockout associated with the thermal model, or starts per hour, or time between starts, all of those things are going to keep us from having to protect for that hot curve. So we want to put it just below the cold curve, and that gives us as much capacity to overload the motor as possible without running the risk of damaging it. Now, unfortunately, in our scenario today, we're going to talk about what we would do if we don't have this data. And there's a lot of data on this curve, and if we don't have that data, we've got to do some other things and make some other assumptions. So let's talk about what we would have to do or what we could do. So let's talk about how we're going to set the motor thermal model if we've got very limited data. So first thing we really ought to set is the pickup value, the pickup of the motor thermal overload. Now remember from the poll question that the pickup is associated with the point when we get above that current, we're going to start to accumulate thermal capacity. So in the 869 and the 469 and the 369, you actually had to set this as a pickup. But in the 869, what you give the relay is a motor full load amps, which I've highlighted in yellow at the top, and a motor overload factor. Now, it's not really used in the thermal model, but it's a good idea to add these things. The motor nameplate voltage and the horsepower, you can add those to, and I've highlighted those. Those are all going to be available from a nameplate. And I show a nameplate to the left here, and that's a typical nameplate, right? The reason it's so hard to read is because all nameplates can be very difficult to read. That particular nameplate, I think when I took the picture, I didn't have a really good angle, and that's why that's not a particularly easy to read one. But nonetheless, we can make out there that this motor has a full load amperage of 114 amps. And let me show you where I'm seeing that at, right? So I'm seeing that right there. So it's 114 amps, and it's asking the relay is asking me for an overload factor, and that is on here as well, and that's given as a service factor, and in this instance we're making that at 15%, so 115. Now, one of the things that has often come up is should we include the service factor in the pickup, as I'm doing here. The recommendation by GE in the instruction manuals is that you would include those pickups in the you'd include the service factor in the pickup there. Now, part of the reason for that this has a long history, but if we look at the electrothermal, the old motor protective devices that we had in existence before we had microprocessor-based relays, those would have included an overload factor in them. The thermal model that is built in the GE Multilin devices incorporates a model that is very close to that old electromechanical thermal model. And it's because of that recommendation inside of the GE manual exists, that you allow for some overload. And allowing for some of that overload does a few things for you. You know, one of the things it does for you is it allows you to overload the motor. Now, the service factor is not meant to be continuous, and that's well defined by the motor manufacturers. but you're not really going to continuously overload this motor. The other thing this does for you is by putting the service factor on there, is it does allow you to accommodate CT error that you might have. So that's why that it's a combination of an ability to overload, a inherent conservative nature built into the overload curves, and 100 years of history of these overload curves properly protecting the motor, that overload factor comes in there. And so that gets our pickups and motor overload factor. So we've got some of the hardest settings set. Now we need to choose a curve, and that becomes a little bit more complicated.
In an ideal world, what we would typically do is we would have this curves, these damage curves that are shown on the screen here. You know, there's the stator hot damage curve at the top, and the stator cold damage curve at the top. Down below that is the rotor hot and cold curves. And in an ideal world, what we would do is we would place our standard curve just below that cold curve. Now, if we've got those curves, that's what we're going to do. Reason we're going to place it just below the cold curve is because for the protection of a hot motor, we've got things like the start inhibit, we've got starts per hours, all those different things to protect that, and that's why we put it below the cold curve. Now, in our situation here, we don't have that data, right? We don't have these curves that we're looking at here, and that's a little bit problematic. So what do we do? Well, if we know the lock rotor time, either hot or cold, if we know the hot lock rotor time, what we know is we know that point that I'm identifying as the safe stall time. So if we have that point, either hot or cold, what we can do is we can place a standard curve just below that point, a standard motor curve. Now, we don't know what's happening up in the running portion, where we exist, how much margin we have, things like that. But because this is the only data we have, that's what we have to go with, and we can put it just below that. Now, the next question becomes, well, what do I do if I don't have that safe stall time, and I don't have that point that I've identified there? Well, one of the things that we could do is we could put some settings into the relay, and we could start the motor a few times. Now, inside of the record, in an 869 and an 859, there's a section records, and then there is start statistics. And every time that we start the motor, we populate those start statistics. And so these are statistical averages. And what we can do is we can start the motor a few times, and we can look at the statistical starting current, the average starting current, and we can also look at the statistical starting time, the acceleration time, basically. And what that does is that gives me that lower point that I've got right there, that learned acceleration time and learned starting current. So it gives that point that I'm identifying on the graph. And if I have that point, I know that that's getting into the starting curve. So what I could do is I could set a standard motor overload curve that was slightly above that point. Now, the bad thing there is I don't know how much margin, if I have any margin, between the curve that I'm going to place slightly above that point and the actual damage curve on the motor. So I don't know how much margin I have there. I do know that if I place that curve correctly, I will be able to start the motor, and I will have protection. I don't know how much margin of protection I have, but in this situation, when I don't have any data, that's the best I can do. And in both of these cases, regardless of how I set that curve, regardless of how I set it, I don't know, I can't know how much margin I have. So this is another reason that you always want to do your due diligence and try to get the data, and use the actual data for the motor, the actual damage curve for the motor. And if you can't get that, reuse the information you have from the previous protection device. That's the next best thing. And then if you can't do either of those two things, then you're stuck doing what I've mentioned here.
The next setting that we need to set is a hot to cold safe stall ratio. Now, if we have the hot to cold safe stall ratios, normally that's these 2 points here, this 8 seconds and the 6 seconds that I show on this diagram, and it's the ratio of those 2 points. So in this case, it would be 0.75. That would mean that the thermal capacity used drops to 0.25 when the device has been running for some time. And when it's at its rated temperature rise, that's where it would fall to. In the case where we are not able to determine the hot to cold safe stall ratio because we don't have the locked rotor time cold and we don't have the locked rotor time hot, and we can't get that ratio, the GE manuals recommend that you leave it set to its default setting of 1.0. You say it leaves to the default setting of 1.0, it will fall to a very low value when it's running at its rated temperature rise. But that is the recommendation from GE, and probably if we went to a lot of relays out there in the wild today, we would find that particular setting. All right. The next thing we should do is we should set a unbalanced biasing. And what unbalanced biasing does is it takes the unbalance that we see on our input to the motor. So the voltage unbalance will manifest itself as current unbalances into the motor. And those current imbalances, that negative sequence, the negative sequence current there will cause additional heating in the motor. And we need to be able to model that additional heating. And so this negative sequence voltage, it could be caused by any number of things: loose connections, turn-to-turn faults, system unbalances, system distortion, or even the blown fuse. And for any of those things, we need to provide some biasing for it, some additional biasing. So the way the multiple end devices account for that negative sequence current is it takes that negative sequence current and divides it by the positive sequence current and then multiplies it times a current unbalance factor, which is K here. So the setting is typically a K setting. And the typical values that are recommended are either 175 divided by the square of the locked rotor current, where the locked rotor current is expressed as a multiple of full load amps. So in other words, that's not where I show locked rotor current squared there, that's not something like 3,000 amps or 100 amps or whatever squared. That is a number more like 6.5 because locked rotor current's 6.5 times full load amps. So when you calculate that number is closer to 5 or 6 or 7 than it is to some other number. It's somewhere in that range. In the cases where we don't have a lot of good information, then what we really need to do is we really need to think about being more conservative on this particular setting than typical. And so that would be the second value we show there at 230. So that's going to give us a larger K value, which means we bias the thermal model more. And we're doing that because we don't have a lot of good information. We're making a lot of assumptions. So we want to be as conservative as we can be. So The next thing that we really need to model is the motor cooling. Now, motor cooling, as I said earlier, the setting that we'll put into the relay, the IED, is going to be cooling time constant. And cooling time constant is 1/5 of the cooling time. So if we look at the two graphs up there, one of those graphs is the thermal model when the motor is tripped, and the other one is the thermal model when it's running. Now, if we look at the thermal model when it's running, the actual cooling time on the one to the right, that's about 60 minutes, right? So 60 minutes is probably, this is 60, it's probably closer to 75 because it's still flattening out at 60 minutes. So it's about 75 minutes for the cooling time. The cooling time constant, the setting that we will put into the relay, would be 1/5 of that, which is 15 minutes. Now that is with the motor running. Now the other graph on the far left, that is the that's the cooling time constant, or the motor cooling when it is stopped. Now we expect that to be longer because it will cool faster when the motor is running, because there'll be fans blowing on it, because there's usually fans on the shaft. So expect it to cool faster when it is running, but we expect it to cool to a higher value. That's why we see it cooling to about 20% thermal capacity used. Whereas on the left, when it's stopped, it's cooling all the way down to 0% thermal capacity used, but it's taking a longer time to reach the steady state. So in that case, the cooling time constant is 30 minutes, so it should take it about 150 minutes to cool, and that's about what we see there. Now, this is great if we had curves like this, or if we have a motor data sheet that says cooling time constant is 100 or is 30 minutes when it's stopped, and cooling time, or if we have the cooling time is 150 minutes when it is stopped. We know that cooling time constant is 30 minutes. That's great if we got that information. If we don't have that information, what do we do? Well, there are probably a lot of motors out there that are set at the default values of 15 minutes cooling time constant for when it's running and 30 minutes for when it's stopped. And there are a lot of motors that are set there. That's not a terrible idea, but there are things that we could do. And so what we could do is, if we have RTDs in the stator of the motor, we could run the motor and stop it and see how long it takes it to cool to the steady state or cool to ambient. And then that would give us an idea of cooling time for the motor stopped. We could take 1/5 of that at the cooling time constant, and then we could take that would give us our cooling time constant stopped. We could take half of that, and that could give us our cooling time constant running. And we can get those two values. So let's take another poll question. So poll question is, why is cooling time constant stopped longer than cooling time constant running? And so our choices are because when it is running, the fans are cooling it. When it is running, the heat is sinking from the stator to the frame. It cools, C is it cools faster when running, or D, it isn't longer. So if you choose the wrong answer here, it will mean that I haven't done either. I haven't done a good job, or you can't understand my accent, and I'm going to be really disappointed either way. So everybody, choose the correct answer now. And I'll give you a second or two longer while you mull over your choice and then we'll go look at the poll results. All right, you've had enough time to vote. Let's take a look at the poll results. All right, why is cooling time constant stopped longer than the cooling time constant running? So 81% of you correctly said that when it is running, there should be fans on the shaft, and those fans on the shaft should be cooling the motor, which will make it cool faster, right? 1.7 of you said when it is running, the heat is sinking from the stator to the frame. While that's not a false statement, it isn't the answer I was looking for, because it's always sinking from the stator to the frame, and that isn't necessarily why the cooling time constant running or stopped is longer than cooling time constant running. 14.9% of you said it cools faster when it's running, which is the same thing as A. So 14.9% of you like answer C. It does cool faster when it's running, but the reason is because the fans are cooling it. And then 2.5% of you, you must be struggling with my accent, so my apologies for that. Cool faster because the fans are cooling it when it's running. Okay, so one of the last techniques that I want to mention before we talk about a few other things is the RTD biasing. So we, in the course of setting this up with limited data, we've made a ton of assumptions. We don't really like to make those assumptions, and some of those assumptions may leave our motor compromised. So one of the things that we can do is we can use this motor thermal model, and we can use the RTD biasing. And we should do that, absolutely. If we have RTDs embedded in our stator, and we don't have good data to set the motor thermal model with, we should absolutely use RTD thermal biasing. And what the RTD biasing does is it builds an alternate thermal model based on a minimum value, a center value, and a max value. And those are settings inside of the relay. And so that minimum value should be set to the design ambient of the motor. So in this case, that looks like that is about 40 degrees C. That should be stamped onto the motor nameplate. The center value should be that 40 degrees C plus the rated temperature rise of the motor. Again, that's the value that's stamped on the nameplate. In this case, the rated temperature rise was 60 degrees C, which got us to 100 degrees C, but then we're going to allow 10-degree allowance for a hot spot. So that'll get us to 110, and that should be our minimum setting. So it's rated temperature rise plus design ambient plus a 10-degree hot spot allowance. That's how we got to that 110. The maximum value should be the insulation rating of the motor. And again, the insulation class should be stamped onto the motor, and we should be able to take that insulation class and determine the temperature rating of that insulation. We don't want to exceed that, so that should be our upper value, and that would be the point where we're at 100% thermal capacity used. That'd be the point we'd trip at. So this RTD thermal model shown here, this is an alternate model, but this model won't trip unless we're above the pickup of the thermal model. So one of the things that we should do, or we should consider, is if we have this alternate thermal model, we should consider, how much of that service factor or how much of the overload we want to apply. And if we have this thermal model, we might want to lower that value somewhat. We still want some ability to overload the motor, but we might want to consider lowering it somewhat since we don't have any data and we're not going to trip unless we're over this value. So I highly recommend using the RTD biasing if you have the stator RTDs and that's available. So we're running short on time. So let's talk about some of the relay offerings that GE offers, GE Multiman offers. So on the low voltage side, there's the MM200 and the MM300. Those are both low voltage motor protective relays and control relays with a lot of really interesting control algorithms available in those devices. On the medium voltage side, the 339 is listed there, so it's a very cost-effective platform for a medium voltage motor. We don't list the 369 here because obsolescence plans have been announced for the 369. The planned last time buy window for the 369 is that window, that last time buy window for the 369 is planned right now. It's planned to close in January of 2024. That's okay because the 369 is easily replaced with an 859, which is shown on the far right. So the medium voltage platforms available today and the ones that you should consider using for medium voltage relays that require a lot of protection is the 859 and the 869, and especially the 859 for retrofit of the 369. Upgrading to that 8 series platform that I just mentioned gives a lot of things. It gives superior quality with Class 3 manufacturing. There's accelerated life testing and highly accelerated life testing that goes on the 8 series platform to validate the hardware and the firmware. There is standard harsh environmental coating that is applied to all the 8S relays, and they come with a 10-year warranty. But on top of that, there are a lot of performance things that come with this newer platform of the 869 and the 859. So sub-cycle protection operating time, an eighth of a cycle for a protection pass, 16th of a cycle for the digital input pass, a much better sample rate for oscillography and for the protection. And all of those, both the 859 and the 869 are integrated into the InterVista suite. So with that said, a couple of conclusions. The motor thermal model protects the motor from heat damage by modeling the thermal capacity used. A lot of these old motors, we don't have a lot of extensive data. So learned data and some of the techniques that I've shown today, they're better than nothing, and it gives us a best estimate to give the motor the ability to start, to run, and to not damage the motor. So with that said, I think I have a few minutes, about 10 minutes for questions. Okay, so here's a interesting question. Can we use RTD biasing to prevent startup instead of typical number of starts lockouts? So that was interesting because the RTD biasing can prevent you from starting, right? So if the actual measured temperature calculates or causes the thermal capacity used to be high enough that you don't have the capability of starting the motor, you don't have enough thermal capacity use margin to start the motor, it would prevent you from starting. Now, I think the other part of that question, though, is do I still need starts per hour and time between starts and things like that? What I would recommend is if the motor manufacturer has recommendations on starts per hour, things like that, starts per hour, time between starts, and those things, I would still recommend, even though the motor thermal model has a lockout, my recommendation would be to follow the manufacturer's recommendations. That can become a warranty issue if you don't, and it's always better to follow the manufacturer's recommendations. Yeah, so here's a question. What about if you only have, say, stall time, which is a hot curve? How do you get the hot to cold ratio? In that case, you're not going to be able to. And so in that case, what you're going to have to do is set the hot to cold, say, stall ratio to the recommendation by GE in the instruction manual of setting it to 1 when you don't have that information. Okay, I think I answered that one. What happens if I don't have the nameplate of the motor? Is it possible to estimate the power and nominal current with the frame or form? That's a good question, right? So if you don't have the nameplate, if the nameplate's rusted off, for example, or it's completely illegible, what do you do? I don't know how you would have the other things that were mentioned in that question, like the frame size and the nominal current without that. But if I don't have that, I mean, there are things I suppose I could do. I could start the motor a few times, and that would give me the start statistics, and I'd know the starting current. I'd know the starting time. I could make some estimates around the full load ounce based on that. So if I knew the frame size, the code there, that gives me a range of block rotor currents as a percentage of full load ounce, but it's a range. So I would have to make some estimates. If I could fully load the motor, to something a little bit less than 100%, then I could observe the current and I could see what the current was at that point, and I could know the pickup. And that might be your best bet in that case. But yeah, that's really pushing it. You're really pushing me to come up with ideas if the nameplate is rusted off. Okay. You're using, someone's pointed out that I was, in my settings file, I was using the wrong RPM for a 900 horsepower motor. Yeah, probably was. I was not paying a lot of attention to that particular setting for the RPMs because I was interested in some of the other settings. So that's a distinct possibility. Yeah, so here's a great question. The NEC states that if the motor service factor is 1.15, you can put an overload factor up to 1.25. Is that the case with GE relays? So yeah, so the NEC states that you got to oversize your motor leads. You got to oversize your motor leads, and that's usually at 125%. So you don't want your thermal model to exceed 1.25. You'd never want that. If your service factor is 115, you could go up to 125. What you set your overload at in the nominal state becomes more of a art than a science for the protection of the motor. When you overload, when you allow the overload to go larger, you are allowing your process to overload the motor, which in most instances is acceptable. Now that service factor is not meant for continuous. So the art portion of that is around, do I really want to do that? How much do I want to do that? Do I want to go to the 125%? You never want to go over the 125% because then you're going to exceed you're not going to have your cables protected. But do you go to the full 125%? Again, that's an issue of around the art and science of this. In a motor, in the scenario that we've discussed today, where we have very limited data and I'm making so many assumptions already, I don't know that I would want to go to the full 125% that I could if my service factor was 100 or 1.15, 115%. And it's merely because in the scenario we discussed today, I don't know how conservative or liberal I am in my settings because I've made so many assumptions. So I would tend to err on the side of conservatism in this particular case and not go to the whole 115% that I could go, or excuse me, the 125% that I could go if my service factor was 115. Okay, I think I've got time for one more, so let me find another one. Okay, that's a great question. I'm not going to read that one because that one's so comical. I think that was a joke. Okay. Some very old motors do not list a service factor. What is the best source of data for making assumption on service factor? That's a great question. If we don't know what a service factor is, or we don't know what the service factor is on the motor that we're setting, we don't have any other data. I just said that I wanted to be more conservative. So I would allow minimal overload of that particular motor. I would make the assumption that I do not have any capability to overload that motor. And if that is, and I would make the assumption that the service factor is 1.0, that you don't have any capability to overload the motor. And if that's the case, then if I want to be very conservative, I would set the relay at 1.0 now for my overload factor. Now the problem with that is that doesn't allow me to fully load the motor without exceeding the thermal capacity or starting to accumulate thermal capacity use. So in that instance, I would probably, I'd either set it at 1.0 or I'd set it just slightly above, like 1.02 or 1.03, so that I could be allow for the CP and inaccuracies and things like that, and allow to go to 100% of the motor full load amps without accumulating thermal capacity used. But I would assume that the service factor in that case is you have no capability to overload the motor, so you should set it to 1. That's probably what I would do. I would set it to 1 simply because in the absence of better data, I would want to be conservative. All right. I think that's all the time we have. Those few questions remain, but we'll look at those and get those answered to individuals. Colleen, would you care to unmute yourself and give us your concluding remarks?
Thanks so much, Terry, and thank you everyone for attending and for your patience with the audio issues earlier on. We look forward to seeing you again at our next Tech Talk. This concludes today's webinar. Have a wonderful day.